Hi students, today let's have a look at the physical properties of waves. Physical properties are things like velocity of the wave, the energy stored in the wave, the pressure difference created as the wave travels, all these properties. So let's begin. So what is the velocity of a wave on a string? We've already studied that a wave on a string is a transverse wave. And the most popular transverse wave that we use is the one we create in a string. So what will be the wave velocity in this case? As you can see, this is the wave that is created on a string. We already know that the formula for velocity is velocity equal to frequency into wavelength. But if we want to calculate the velocity in terms of the properties of the string, then the velocity of a transverse wave on a string will be v equal to root of t by mu. Now what is t? T is the tension in the string. In the chapter force we studied, remember, that a string has a certain value of tension in it. What is mu? Mu is the mass per unit length of the string. So if the length of this string is 1 meter and its mass is say 2 kg, then its mass per unit length is 2 kg per meter. But where does this formula come from? V equal to root t divided by mu. Can we derive this ourselves? Let's try. So let's calculate the velocity of a transverse wave in a string, but we'll do it in a slightly weird way. We'll calculate the velocity of a transverse wave in a string from the frame of reference of a man who is moving at the same velocity as the wave. So have a look at this man here. I know he looks a bit crazy, but let's be friends with him for now. So we will calculate the velocity of the transverse wave from this man's frame of reference. And this man will be moving at a velocity v same as the velocity of the wave. Here, you can have a look at him again. So we will perform all our calculations for the velocity of the transverse wave from this man's frame of reference. Why will we do that? Doing that will help us a lot in simplifying the variables involved. I'll come to that later, but for now let's use this frame of reference. Now, if this man were at rest, he would actually see the wave moving. In fact, anyone at rest would see the wave moving with a velocity v. For anyone at rest, the string, however, would be at rest. For example, if you were looking at the string, you would see the string going up and down, and you would see the movement of the wave towards the right. But you would not see the movement of the string towards the right, because as we all know, in a transverse wave, the particles just move up and down. So the string particles would just be moving up and down as the wave moved from left to right. But things are different in this man's frame of reference. In this man's frame of reference, the wave is at rest. That is because he is moving with the same velocity as the wave. And similarly, in this man's frame of reference, the string is not at rest. The string is moving to the left with a velocity v. That is because the man is moving to the right with a velocity v. So in his frame of reference, the string, even though it is actually not moving to the right or left or anywhere, in his frame of reference, the string will be seen moving to the left with a velocity v. Understood? I know this might sound a bit complicated initially, but think about it and you'll understand. And I'll repeat anyway. In this man's frame of reference, the string will be moving to the left with a velocity v, and the wave will be at rest. So this man will not even see the wave moving. He'll simply see the string moving like this towards the left. Now let's have a closer look at the string. Here, let's take a portion of the string, this portion. What are the forces acting on this portion of the string? Let's write the equation of motion of this portion of the string. That will help us find the velocity of the string in terms of the properties of the string. Let's magnify this portion. Here it is. That small portion has now been magnified. This small portion we've taken is so small that you can call it an element of the string. It's an infinitesimally small portion of the string. Here it is. What are the forces acting on this small string element? There's of course tension from the other parts of the string, and the velocity of this element is v towards the left. Why is the velocity v? Because as I said, we're performing all our calculations from the frame of a man who is moving at a velocity v to the right along with the wave. This man will see the string moving towards the left with a velocity v. That's the reason that the velocity of the element is v towards the left. Let the length of this element be delta L. Delta L is a very small quantity because we've just considered a very infinitesimally small portion of the string.